I hope you can hear me. Cool. Hi, everyone. My name is Andrea. I'm from Riverlane, and today I'm going to be giving you a two-part talk together with my colleague Aniket on the QEC interface for real-time quantum error correction. So in my part, I'm going to cover the main motivations for having such an interface, and my colleague will go deeper into what we're actually proposing this interface to look like. We're going to try and deliver these two parts together, and then we'll be happy to take all of your questions at the end. So to start with a little bit of a background, we all know that qubits are inherently noisy. So for us to perform some useful quantum computation, we need to combine many of these physical qubits, tens to hundreds of physical qubits together to actually form a single logical qubit. But during our computation at the logical level, these individual physical qubits have errors happening on them. And we need to be able to understand when these errors are happening so that actual useful quantum computation can be achieved. So what that means is that during a quantum computation, we're performing something that we're calling the QEC cycle. So what happens is that the control system is obviously applying some sort of pulses and controlling the qubits. And we're continuously reading out some of these qubits and sending them to something like a decoder that is trying to understand what are the errors that occurred on those physical qubits. And based on this information that we're receiving and decoding, at the right point, we can send a correction back to the control system saying that a specific conditional operation has to be applied to the underlying physical qubits. So this implies that we need some sort of constant real-time data passing between the control system and the dedicated decoder or the QEC system. So what we're proposing is that I'm going to now control from here, I hope. There. So what we're proposing is an interface that sits in the control system and also in the dedicated QEC system. So this interface allows these two systems to communicate in real time and send this data between each other. We're developing this interface with a lot of consultation from our hardware partners and control system partners. So I would really encourage you to engage with us in this conversation to figure out what are the best ways that these two systems can communicate. So on the right-hand side of the diagram, we see Riverlane's delta flow, which is our QEC solution. And on the left-hand side, we have a control system that is talking to the qubits. When we zoom into this interface, you might notice that we're proposing arrows going in both directions, and that's really important. The arrow at the top signifies some sort of configuration data that our system is receiving before an experiment is being executed. And the bottom arrow is bidirectional because we know that during useful quantum computation, we will not only have to accept data in real time from the control system, but we'll also have to tell the control system to make a conditional operation during the computation. So we need to support a bidirectional link in real time. And this is what the interface is also proposing. So how are we proposing this interface? We're writing a formal specification that is designed to be generally applicable. We would really like this to be an open de facto industry standard in the future, where all of our products obviously implement the specification to the most recent published version, and we encourage both our control system partners and other players in the quantum error correction ecosystem to adopt this specification. In broad terms, this formal document describes the data format that is exchanged between the two systems, and also the runtime states and the parameters that needs to be kind of determined to communicate these QEC-specific messages. You might rightly so ask the question of why are we proposing a new interface if in the engineering world we already see a lot of other interfaces that exist and seemingly could be applied. So any general interface is usually composed of three layers: the physical layer, the data layer, and the protocol layer. Fault-tolerant quantum computers are hard real-time systems. We require a low latency link and a high throughput link. And the current protocols are just not quite designed for these. For example, Ethernet has quite a high overhead in its data packets, and that leads to a lower latency. Or something like PCIe implements retransmission of data, which increases reliability, but that also makes it non-deterministic in time. The other approach we could take is mix up the existing layers from interfaces. So take a suitable physical layer and then a different suitable data layer and make like a combined interface. However, that would be quite a patchy solution and could lead to poor performance, which we just don't want for our systems. You might also ask why push for an open standard and something that is widely adopted. We think there's a huge advantage in basically doing integration work once at the beginning, and then using the same interface and the same integration work, and just upgrade both of the systems, the QEC system and the control system, independently, without having to redo that work. So by having an open, widely adopted interface, this integration and continuous upgrades are much more simple. So that allows for long-term interoperability of the systems, and it also allows all of us to focus on the respective challenges that we have. So the focus remains on the science, on the engineering, while the integration work is done easily upfront. This is the overview of the interface that we're proposing. So I will give you a brief description of the layers, and my colleague will then dive deeper into each one of these. So we're going to start from the bottom and move up. Our physical layer is basically the carrier for these data packets over a physical interface. It handles everything on the classical error correction side so that it basically creates a single reliable link between the control system and the QEC system. It's also something we're providing as an IP to our partners to ease this integration between the two systems. The data layer basically tells you what does the format of the data look like that is exchanged between the two systems. And it also specifies how these two systems address each other during runtime. And then we have the protocol layer, which is very quantum error correction specific. It allows these systems in real time to know what operation is being performed, if logical branching has happened, and whether they need to switch any of kind of the computation that they're currently performing. So that's the most quantum error correction specific layer of the three. Now, I'm sure you have a lot of questions about these layers, so that's why I'm going to hand over to my colleague, who will give you a lot more detail on these.
We need to switch the slides.
We're going to switch the slide.
Yeah.
Okay. So here's
That next one. All right.
Hello. Can you hear me? All right. Thanks, Andrea. So Andrea already talked about how a QEC cycle works and why we are introducing a new interface here. So our long-term vision is widespread adoption of the QEC interface. We appreciate that both the QEC system and the control system can be built in many different ways. The architecture can be very different, so our specification is very flexible. We take only one assumption here, that both these systems are made of a distributed set of nodes. Now, what do I mean by these nodes? One of the simplest way to put it, so for a control system node would be the smallest addressable unit within a control system that generates or aggregates readout data. Similarly, a QEC node would be the smallest addressable unit within a QEC system that can perform QEC computations. Now, as I move further through the presentation, the role of these nodes in our specification will become clearer. So Andrea already talked about we having three layers in the QEC interface. We have the physical layer, the data layer, and the protocol layer. So I will dive a little deeper into them. So let's start with the physical layer. The main objective of the physical layer is to have a low latency, high throughput, reliable communication between two FPGAs over a physical link. And also, first of all, these FPGAs can be from different manufacturers, different product families, because there is no guarantee that the control system and the QEC system would be using the same FPGA. Secondly, they will have their own reference clocks, so these are completely uncorrelated. I mean, they can have completely uncorrelated jitter. So to solve this problem, we have a custom high-speed physical layer IP that can operate at 12.5 Gbps link speed. Now, this IP kind of abstracts away all the low-layer complexities like data serialization, then clock recovery, error detection, line alignment, all of that. And it exposes a very standard axis streaming interface to the user logic. And we provide this IP to our partners, so they can just like use it in their system, and the integration becomes very simple. Right. Next, I'll move on to the data layer. The QECi specification is very extensive. There's no way I can cover everything within this short period of time. So let's try. So we have the data layer. So the data layer has 64 bits. So every data packet is 64 bits, 32 bits for the payload, and 32 bits for the header. Now, the payload changes based on the packet type. I'm going to be focusing on the header in this talk. So first, we have the direction field that specifies whether a QECi packet is going from a QEC node to a control node or the other way around. Then we have the command. The command field kind of specifies the type of packet. Within QECi specification, we have 4 different kinds of packets. We have CSR requests, configuration packets, status packets, and readout packets. So later in this presentation, I will walk you through a mock experiment, and I'll show you how you would use these different kind of packets within a QEC experiment. OK, and then we have burst support. So this could be quite useful. For example, a control node could aggregate a lot of readout data together and send all of that with a single header, and thus saving some bandwidth on the physical link. And then we have the address field. So we have 16 bits reserved for the control node address and 8 bits reserved for the QEC node address. So this way, we know exactly where the packet came from, exactly where it is going. A little bit more details on the addressing scheme. So I already said in both the systems, we visualize the nodes to be the lowest addressable units. Now, multiple nodes together form an L0 group, and then multiple L0 groups together form an L1 group, and so on and so forth. We support casting. So let's say if a control system node wanted to talk to a specific QEC node, it could use unicast mode. Or if a control system node wanted to send a data packet to all the QEC nodes within the L0 group, it could use a multicasting mode. We also support multiple levels of multicasting, all the way to broadcasting to all QEC nodes. And this is applicable both sides. Right. Once again, that was like a very short summary of the data layer. If you have questions, please find us later. Now I'll jump into the protocol layer. This is where things get interesting. I'm going to walk you through a mock experiment and show you how everything kind of fits together. Right. So the protocol layer introduces these 2 concepts. The 2 key concepts are frames and observables. But before I jump into that, I want to take your attention to the mock experiment. The reason I call it a mock experiment is because this doesn't really represent a real-life QEC circuit. It's not a logical operation, but it kind of emphasizes all the essential building blocks that we need to perform one. All right. So we have space here, and time moves upward. Right. So let's start with 2 physical patches. So these are 2 physical patches that represent, let's say, logical qubit 1 and logical qubit 2. In each patch, you could have hundreds of physical qubits. So each patch is controlled by multiple control nodes. Now, in protocol layer terminology, we call these patches frames. And for this example that I'm presenting, we will consider 1 QEC node per frame, keeping track of the errors. Right. So how do we start? So so the control system initiates the whole process. So from now on, when I say you, I mean the control system. So you start by initializing these 2 frames to a particular state. And then you configure the QEC nodes corresponding to the frames you configure the QEC nodes. And by configure, I mean things like you could possibly set the path size. And there could be many other configurations as well. But yeah, that would be one of the simplest examples. So once your configuration is done, the control system starts the experiment. So you start the experiment by writing a register to the corresponding QEC nodes once again. And then once you have started, this is a superconducting example. A measurement round occurs every microsecond. This is a physical circuit that the control system needs to take care of. And then on every measurement round, all the control nodes that are responsible to control these physical patches kind of collect all that data, readout data together, and they send all that readout data to the corresponding QEC nodes. And the QEC nodes keep track of errors. Now, when we come to the end of that section, once again, the control system node goes to the QEC node, says, OK, we are done. And then it retrieves an observable. An observable is a single bit value that says if an error has occurred during these measurement rounds on that logical patch. And then based on this observable value, sometimes in some situations, you may need to perform a gate operation on a different logical qubit. So I hope that was clear. Now I want to talk through a real logical operation. So here we are trying to apply a T gate to a logical qubit. This involves magic state distillation, like in the red area. I'm not going to get into that, and I don't have a. Is there a? Okay. So we have two logical qubits there, and time moves this way. So first we perform a logical C0 between them, and then we get an observable on the logical qubit which is below, and based on that observable value, we perform a conditional S gate on the logical qubit that's on the top. So this is how we perform a T gate. All right, so that's, oh, I'm good, thanks. That's all the slides I had, but if you're interested to learn more about how we do quantum error correction at Riverlane, please come talk to us at booth 174. Thank you.
Yeah, I have a question. So for any real-time system, there's always an inherent latency. So I'm just wondering, how much latency do you have measured in your system, like or the delay from propagation to transmission?
So we haven't yet run an experiment on real qubits where we would be able to do the full loop. We're in the process of doing those real-time experiments, but our current target for latency in terms of internal development is around 20 microseconds. That's where we want to get to.
How much does this interface depend on the underlying code, methodology for doing logical operations, et cetera? Is it agnostic to that, or?
Yeah, it is quite agnostic. Because, okay, so if you think about the physical layer, that's just transferring data. And then we have the data layer, which is, again, quite agnostic. Because then you are just transferring readout data, and then that readout data could come from anything. So you could have superconducting systems, you could have AMO systems. Yeah.
So is there an agreement that has to be between these different layers? Like, you need to do this decoding on this because it's,
yeah,
LDPC code versus a surface code.
Yeah, some of that information comes through the configuration messages that we send before the experiment. Yeah.
Okay, gotcha. Thanks.
Let's thank the speakers again, please.
Thank you.